Thank you, everyone, for coming today to Communication Across the Curriculum, or CAC. And we welcome today Aaron Clevenson, who teaches astronomy. And we've been trying to get Aaron to talk at CAC for several semesters. And so I'm glad that you were able to fit it in this time, Aaron. Thank you. And Aaron's title is Black Holes, Dark Matter, and Dark Energy.
Okay, so most of you know me for one reason or another, but let me just tell you a little bit about myself. I've been teaching here as an adjunct astronomy professor for 13 years, and I actually built the programs, designed the programs that we're using here. And in addition to that, I'm the observatory director at the Singularity Observatory. And since none of you know where that is, it's over in Humboldt, I think just east of the runways. And we're open on the first Friday of every month from sunset to 10 p.m. to the public, so you should come join us. But today, I want to talk about black holes, dark matter, and dark energy. And so I was putting my slide deck together, and this is it. I only have one slide because there's no point in having more because all of them are black. So I had nothing to talk about. No, I'm kidding, actually. So I had to start with a little levity. What I will not be talking about today are gravitational waves, and I'm looking for an invite to come back because I'd much rather talk about that. Because this is so cool. Now this is, and I gotta just tell you one reason why you should invite me back. I'll take us back to about Galileo. So for the last 400 years, everything we have learned about the universe, actually it's longer than that, for the last 100,000 years, everything we have learned about what's out there in space, beyond the Earth, is through electromagnetic radiation. And in 2015, we discovered the first gravitational waves. And the excitement behind that is, it's in its infancy. We don't know anything, hardly. But it's completely different. And so a whole new realm of astronomy. That's just, so exciting. And sadly, I can't afford a gravitational wave detector, but okay. So the question is, why did I pick this topic? So there are lots of mysteries in astronomy, lots of stuff we don't know, and astrophysics. I'm just going to call it astronomy. But there are these three things that we actually know absolutely nothing about. We can see some information from them, we learn a little bit about them, but absolutely nothing. And I will show you why. So that's what I want to talk about today. And I've got an example of other things that fit into this. So for example, air. Now we're all intelligent and have enough background knowledge that we know it exists, and so that's not a weird thing. But if you think about it, we can't see it, we really can't feel it unless the wind's blowing, and that's later on. And we can't smell it unless it's polluted. So we're sitting here, what proof do we have that air exists? But we can detect it from other things that happen because of the air. So for example, the wind blowing, we obviously breathe it, so there's sort of air exchange going on there. And so we can observe it indirectly. And that's what we have to do for these other things that we know nothing about in astronomy. So it works exactly the same way. The nice thing about air is we've evolved to the point where we know something about air. We know what it's made up of, we know what it looks like, which it doesn't, but we've got all that. And so hopefully someday we'll have this for the other thing. I also want to cover a little bit of background. So I've got some science folks here, and so even math folks. What do you do?
I'm a retired geophysicist.
I've got basically all math and science folks. What do you do?
English.
English, all right, so this is for you. And you probably already know this too.
No, I doubt it.
I wanted a little bit of background.
No math.
No math. There is no math in this presentation whatsoever.
Okay.
I want to just touch on two things real briefly before I start, because it's a very important piece of this, and I'm going to say things that I don't want there to be any misunderstandings. So the first thing is scientific theory is not just any old theory. It's not your father's theory, is what I was going to say. But it's true, because a scientific theory has to meet four requirements. It has to be testable, it has to be continuously tested, it has to be simple, and it has to be elegant. So the first three of those are easy. What they mean by elegant is a little harder to explain. I'm not going to mess with it. But the way I kind of interpret elegance when I think about scientific theories is it magically, all of a sudden, makes all these things make sense. The simple is easy. The fewer variables you have in it, the simpler it is. There is a caveat, though, and that is scientific theories can't be proven. They can only be disproved, or disproven, whatever the proper term there is. And the reason for that is you have to continuously test them because you can't test every possible case. So there's no way that you can ever actually prove it to be a fact. But all it takes is one exception to disprove it. The second thing I want to just mention briefly is the cycle that you go through. And typically you start at the top, but you don't have to because the circle keeps going around and around. But normally you see something and you say, and this is kind of the basis for this talk, we've seen things that don't make sense. So you've seen something, it's new, it's different, you don't understand it, and you come up with a theory, scientific theory in this case, of why you think that is the way it is. And then once you've got that scientific theory, then that theory makes a prediction, and you go back and you observe to see if it's true, you test it. So that's the cycle that we always go through for scientific theory, and all three of the things I want to talk about today fit into that. The problem is we're great at making predictions, but we have not been able to go back and test. So they're a little bit premature to call them scientific theories, but the intent is that they will be tested. So the first one is black holes, and if we were to see a black hole, now the problem is they're so far away, and this part that's black is so small that we can't see it from here. The resolution is just not good enough to see it, but if we could get close enough without getting sucked in, we would see nothing. It would be black, a black hole. And around that, you would see matter that's slowly being pulled in, but if you look right at that black hole, you don't see anything. So let me elaborate on that a little bit without getting too technical and no math. The parts of a black hole. So you've got this disk of material outside here called an accretion disk. So it's being sucked in, it's being accreted onto that black hole. We'll come back to this. You have jets that come out of the magnetic poles. So if you think about it, you've probably seen a picture of the Earth where it shows the magnetic field lines. And of course, that's where the auroras happen. The Earth's not rotating very fast, and although it's a nice magnetic field, it's not that strong as far as this would be concerned. So we don't see any weird effects because of our magnetic field other than the auroras. But black holes have a very strong magnetic field, and they're rotating very fast. And when that happens, you get charged particles that get caught up in that magnetic field, and instead of like on the Earth, they come falling in and we see these pretty colors. There, they get shot out at very, very fast speeds, relativistic, almost the speed of light. And so you do see these jets of matter. Now, they're not coming out of the black hole. It's stuff that didn't quite make it into the black hole, and it's being shot out by the magnetic fields. And then we have this thing here called an event horizon. And it's got a few different names. Do I not have another picture? I don't. All right, I'll have to talk from this one. And then there's one more piece that we can't see, and this is hypothetical. We believe it has to be there, but we can't prove it. And that is in the very center of that event horizon, we have a singularity, the black hole itself. The event horizon that we can't see, but that event horizon is the distance from that center where the escape velocity is the speed of light. And since nothing can go faster than the speed of light, even light can't escape. So we can't see anything from a black hole. Okay. So why do we think there are black holes? And it starts out with, if you look at a star like the sun, physicists or astrophysicists sit down and they say, when it runs low on fuel, we're not going to have fusion to keep it puffy like a star should be. It's going to start to collapse. And what's going to happen? Well, in the case of our star, it's going to collapse into this giant diamond, basically, because it'll be carbon at that point. And very tightly packed, very hot, so it's like a carbon, it's like a diamond ember at that point. But that's it. But what if you get bigger than the sun? So these theoretical physicists sit down and they say, and they've come up with some limits. So if it's 1.4 times the mass of the sun, so this is the piece you're left with, if it's 1.4 times the mass of the sun, you're going to overcome the electrons trying to stay out of the nucleus. And it's going to squish those atoms down and force those electrons into the nucleus and basically end up with a big ball of neutrons, or a neutron star. And that's called the electron degeneracy pressure, because those electrons, they're negatively charged. The core, where the protons are, is positively charged. They really don't want to get together. But if it's 3 or more times the mass of the sun when it collapses, what you end up with is it doesn't stop at the neutron stage. That gravity is so strong that it continues to pull it in more where it overcomes the neutron degeneracy pressure. Well, that's where what we know collapses. Because once it does that, it collapses. We know of nothing that would stop it from collapsing down to a single point, a singularity. And when it does that, it ends up being smaller than that event horizon. So we can't see anything inside. So there's no way to know what's really going on in there. Okay, so why do we think they exist? You know, that was theory, why we think they should exist. But the question is, why do we actually think they exist? I forgot to set this up, but we're going to run that because it's so cool. So let me just pause for a second. And the last time I tried this, it did not work, which is not going to work this time either. Okay, so come on. Here we go. Copy that. Drop it there. Because it is so cool. So these are stars near the core of our galaxy. And of course, this is a computer simulation, basically. But I want you to watch what the stars are doing. So they're doing all kinds of weird stuff around that X, sort of an X. They're following these orbits. And this is real. There are stars in the center of our galaxy that we can see with a radio telescope. And they're doing this. And if you look at them, they're all orbiting around something that we can't see. There's no evidence of it at all. I just thought that was a wonderful, wonderful visualization of what they see when they look with radio telescopes over time. All right, so back to the main event. So we do use radio telescopes, and we look at the core of our galaxy, and we see this kind of activity going on around something we can't detect. It's not giving off light. Well, we can't see light in the core of the galaxy anyway, but it's not giving off things that we can detect with radio waves or any other frequency of electromagnetic radiation that we're using. So we end up with stars that are orbiting nothing, which that's not how it works. And when you look at those orbits, you can calculate the mass of that thing in the middle. And the thing in the middle is gigantic. So it's a supermassive black hole. So we think they probably do exist. The problem with black holes is there are only three things you can measure. You can measure mass, which I understand how you do that. You look at the stars orbiting it and you say, okay, we can calculate the mass. Spin velocity, and the way you get spin velocity, and you have to get close enough to see this, but if you look at that accretion disk that's rotating around it, the speed of that, very close to the black hole, represents the speed that the black hole is spinning, because it'll be very close. The one I don't understand is how do you get charge? But charge would be the other thing that you could tell. Positive, negative charge. Obviously, we haven't done that. And I can't think of a way you would do it remotely. You would have to get up close and actually check it out. So a few other things. They emit no electromagnetic radiation, none whatsoever. We can't see anything inside the event horizon. And the real problem is we have scientific theories that we use trying to explain the universe in physics. When you get inside a black hole, those laws don't work. Those scientific theories don't work. As a result, we can say, well, it makes sense, you can extrapolate that this is going to happen. It would collapse to a singularity. But does it? We don't know. So there are some issues. So like I said, we don't know anything, actually. You know, all of this so far has been speculation. We've seen jets. We have seen stars orbiting around those black holes in the center of galaxies. But that's it. We really know very little, or next to nothing about them. But they must exist. So the second topic was dark matter. So I could have had a black screen for this one too. This is worse. These are going to get worse as we go, by the way. This is worse because we can't see it. So it's, you know, just like a black hole. We can't see it. It doesn't interact with normal matter except through gravity. And that's why we think it's there, is because of gravity. But we know nothing about it. We think it's everywhere. But if it's not normal matter, my conclusion is we don't even know how you would detect it, if you could, because it's not normal matter. It doesn't interact with normal matter except by gravity. So we've observed a few really interesting things. we look out there and we see these big clusters of galaxies. So we're in one of those, but we can look at other ones as well. And we see how those galaxies behave inside that cluster. And by doing that, you can say, okay, I see what's going on. There's got to be more mass there than we can see. But we can't see it, so we don't know anything about it. There are, and we're going to go into most of these in a little more detail. Gravitational lensing, I'll talk about that when we get to that slide. Galaxy rotation curves. This one I don't have a slide for, so I'll talk about it just briefly. If you look at, there are two main types of galaxies. There are elliptical galaxies, which are big balls of stars, where the stars do their own thing, but they all orbit the core. And then there are spiral galaxies like ours, the Milky Way, which are the pretty ones. And, but hey, you know.
Bring it on, Aaron.
The pretty ones. Okay. I can say that. You know, if somebody shows up from an elliptical galaxy and wants to take issue, I would love to have that discussion. Anyway, but if you look at elliptical galaxies, you can study the motion of those stars. And based on the motion of those stars, you can come up with an approximation of what the mass is of that elliptical galaxy. And what we find is those stars are behaving like there's more mass than we can detect using the stars. So it opens up some real big questions. And then the cosmic microwave background radiation, that'll be a recurring theme. We'll talk about that when we get to dark energy as well. This is stuff that was predicted a long, long time ago, and then everybody forgot about it. And then they discovered it sometime in the 1900s. I don't know the exact date, but they discovered it, but they didn't realize that was what they discovered. They thought it was noise. And they couldn't find a way to get rid of the noise. And what they ultimately discovered was, sure enough, this is the stuff that was predicted, 100 years before, which is kind of cool. We'll talk about that too. Okay, so what's going on in galaxy clusters? Well, there's some really cool things. So first off, you can look at the velocities of those individual galaxies, because they orbit each other, just like planets orbit the sun, except in this case, they're more the same mass. And because of that, they've got similar gravity, so they tend to orbit each other as opposed to everybody orbiting one particular one. We can also look at X-ray emissions from hot gas in the cluster. So you've got the cluster, you've got galaxies, they're behaving normal, and then you get dust and gas throughout, and it's giving off X-rays. And by studying those X-rays, you can see things that don't make sense based on the normal matter that we can see. So it implies, again, that there's something else there that we just can't see it.
Aaron, why X-rays and not like another type of energy? Why not ultraviolet or why X-rays specifically?
Good question. The only thing more powerful than X-rays are gamma rays,
Yes.
and they're too powerful to focus. So
if you're focused on them, you might be in trouble. So.
Well, if I look, we do have gamma ray detectors, but it's sort of like taking a piece of film without a camera, exposing it, and then expecting to see something. So you don't get any kind of really discrete image. And the reason is they're so powerful that we just don't have a way to focus them. So that's not useful. That would be useful if we could do it, but we can't do it.
Okay.
So X-rays are very powerful, and we can do it. They're very fancy telescopes that do that, but it's really cool, and they are able to focus X-rays. Everything else is lower power. And so it's not as exciting, and it doesn't tell you as much about high energy events going on inside the clusters.
Okay.
So X-rays are just better for that, but it also means you have to put your telescope in space, because most X-rays don't make it to the ground. And then we already talked about this one, but gravitational lensing, which is really cool, and I have an example. So we'll just go on to that example.
We like gravitational lensing.
You like gravitational
Yes,
lensing?
we do.
Okay. So the one I like the best, I have never actually seen this or taken a picture of it, but supposedly I can. It's called the Einstein cross. So in that picture, the dot in the center is a galaxy, and the 4 dots around the outside are the exact same, much more distant galaxy. It's actually a quasar, but a much more distant galaxy. And they know they're the exact same one because they look at them with a spectroscope, and they study it, and the spectra for each one of those 4 is exactly the same. And that would never happen in nature. So it can't be 4 different things, it's got to be one. And so what you get is 4 images. This is gravitational lensing, 4 images. What that tells me is that galaxy in the middle probably, my guess would be, has 4 spiral arms. And that's why you get 4. That's pure speculation, but that's my opinion anyway. Another example of the same kind of problem is over here in this galaxy cluster. So the things that are roundish are galaxies, and they're all over the place. The things that are these arcs, which are also all over the place, are gravitationally lensed quasars that are further back. So, the galaxy cluster itself, I don't know the exact answer, but I would guess it's, at most probably 5 billion light years away. The arcs are from quasars that are probably closer to 10 to 12 billion light years away. And they've studied these as well and noticed the same thing. A lot of them are related to the same quasar. So, really obvious. I have no hope of ever personally seeing this, but I think it's pretty cool. And like I said, that should be visible. Another way to look at gravitational lensing is to go out there and look at where we think dark matter is. So this is all about dark matter. So this is a map of where they think dark matter is. The brighter the color, the heavier the concentration, the more mass we attribute to it. And what they're looking at is a piece of sky, and there's galaxies and all kinds of stuff going on out there. And we see these effects coming through the galaxy clusters. And based on that, they're able to come up with a map that looks like this. So this is very theoretical, obviously. We haven't been there. We haven't seen or touched the dark matter. But we're able to do things that let us map where we think it is. So it looks like it's there. We're finding lots of supporting evidence. Another way you can do this is galaxy rotation curves. So now we're back to the pretty spiral galaxies again. And a spiral galaxy, as you start in the center and work your way out, the orbital speed of those stars, individual stars, is related to the mass inside their orbit. So if you're in close, the mass isn't going to be very high, so you're down here. And as you move further out, you get more and more. And when you get up to about here, Kepler and his laws predict that you should have a decline. Because now you're moving further and further out, but there's no additional mass, or very little additional mass. So you can't support the speeds. What we actually see, the dots here, are scientific data that's been collected, empirical data for the Milky Way Galaxy. And so when you study it, what you see is it doesn't drop off. That means there's a whole lot of mass out there that we can't see. And we don't know what it is. And they have some ideas of what they think it might be, but until you get a piece of it, you don't really know. And then the last one was the...
It's our baby picture. That's our baby picture.
That is our baby picture. This is the highest resolution baby picture. So this was taken with one of those 20 megapixel cameras as opposed to a 3 megapixel camera. This is the most recent one that I could get my hands on. And the different colors represent different temperatures. So what we're looking at is its radio waves. And all electromagnetic radiation ultimately leads back to a temperature of the object you're looking at. And so this is very, very cold. And although that's a very pretty picture with everything from dark blue to bright red, the reality is on the temperature scale, the different colors are microkelvins. So 1 Kelvin is equal to 1 degree Celsius, which is roughly equal to 2 degrees Fahrenheit, just to put that in perspective. And micro is 10 to the 6th.
Yeah.
So tiny, tiny little fluctuations, which poses all kinds of other problems for physics, because you'd expect it to be fairly flat, completely flat, and it obviously isn't. So just amazing. And those fluctuations imply there's something there that is causing different effects of gravity that we can't see. We know there are no stars at that point. And stars did not exist that far back. So it poses some interesting problems. What is causing the clumping?
But what, okay, can I ask you, but even if the
Absolutely.
stars didn't, was there still matter at that point that you were discussing, like, dust and even atoms, but no stars, or, I mean, even matter, even on a small level, has effect on other matter, right?
That is true. So at this point, my answer would be yes. I'm trying. Now you've asked me a question.
I know.
I've got to get data from 2 different places
Okay.
upstairs here to see if I can put it together. But my answer, without checking my notes, would be yes. Don't test me on this later. But, no, my answer would be yes. Matter would exist, but it would be in the form of a soup. So it would, in fact, it was a soup prior to this point, because this is the point where it went clear.
Okay, so that's my question. So before that, it was orange, right? Did it glow orange before it went? Was the microwave?
Why orange? That's a
Because
nice color, but I just want.
Because it redshifts.
So yes, that's true too. In fact, this is redshifted. So I'm drawing back here on really weak memories, but okay.
I'm not trying. I promise I'm not trying to.
What
I
we're picking
love
up
this
right
stuff.
now is radio waves,
Okay.
and it is redshifted from infrared.
Yes.
Okay, so it would have been infrared prior to this point in time, but we couldn't have seen it because prior to this point in time, the electrons were not attached to atoms,
Yes.
and without the electrons attached to atoms, it's opaque. You can't see
Okay.
it. So that's why this has to be the first thing we can see with electromagnetic radiation,
Huh. Okay.
which is why I'm excited about gravity waves, because they'll go back further than this. So, tough questions. But
I'm
okay.
sorry. I'm sorry.
Sorry,
You,
good
see,
question.
you're talking about something I love and I don't know that much about it, and you're.
Well, and neither do we. That's the problem with all this is, it's really very much unknown. The story that goes behind this and the succession of finding out that information is also fascinating, but I don't have time. Okay, so where is it? So this is another picture of the Milky Way Galaxy. We're in the center here, the part that actually looks like a galaxy. And it doesn't show up real well. I'm not going to turn the lights off, but it doesn't show up real well. But there's this blotchy looking blue that goes around the galaxy. And that's what they think the dark matter map roughly looks like. And so you have the galaxy, and in our case we're a spiral, so we're kind of flat. And then the galaxy has a halo. And in that halo are things like globular clusters and other cool stuff. But outside of that halo is where we have the dark matter halo. At least we think that's what's out there.
Aaron, are we drawing that conclusion based on observations of other galaxies? Because we can't tell that from within, can we? Or
Yes.
we can't.
So for those of you who don't know where he's coming from, I do. You can't see the shape of the forest when you're standing in the forest, because all you can see are trees. So if you think about our galaxy, it's the same way. We're standing in the middle of the galaxy, all we can see are stars. We can't see the galaxy as a galaxy. We don't know what it's shaped like. However, what they have done is surveys with radio telescopes all across the galaxy, and they've come up with, this is what our galaxy looks like. And so it's, I don't want to call it simulated because that's not the right word, but it's a representation of the data for our galaxy. Again, this is rather theoretical, but they can also see the effects from that part, that dark matter halo outside the galaxy.
And can they do comparisons with other galaxies to see if this is a typical situation? Or?
Yeah, in fact, the data would be better from other galaxies. So if you look at the Andromeda Galaxy, but again, a lot of what we get when you're looking at an individual galaxy is that rotation curve. So it basically tells you there's stuff out there, but it doesn't give you detail. That's why this is kind of nebulous and you can't really tell what's going on because we don't have accurate
But that
data.
dark matter halo is everywhere, isn't it?
They believe it's clustering around galaxies
Okay.
and clustering in amongst galactic clusters.
Okay.
So, and much more of it around galactic
And that
clusters.
makes sense because of the mass that's, yeah, because, exactly.
Yeah.
Exactly.
Okay. This is very speculative, as far as the pictures.
This is super wonky cool.
Okay, so that's dark matter. This brings us to dark energy, which is even worse. Yeah, you came right, you were very excited about this. So, same kind of stuff. We can't see it. We have no clue where this came from. Dark energy, and we know absolutely nothing about it. But again, just like dark matter, we can see effects that it's having on the rest of the universe. So what we think we know is when we look out there into empty space, we believe dark energy is everywhere and it's homogeneous. It's the same everywhere. So what we're equating it to is the energy of empty space. Okay. It's very weak. It's much weaker than gravity, which is the weakest of our four fundamental forces in physics anyway. So it's very, very weak. So when you look at a galactic cluster, and I'll just make it simple, us and Andromeda, Andromeda is not moving away from us because of an expansion of space. It's moving toward us, but that's because the gravity is still strong enough to pull us toward each other, and it overcomes dark energy. Okay, so not very strong. It also only seems to react through gravity, like everything else, but kind of in the backwards way. It's like anti-gravity. Cool. That's kind of cool. All right.
Oh.
So unlike matter or energy in space, as space expands, the density of dark energy stays the same. So let me give you an example of what I'm talking about, because I just said that and it didn't quite make sense. Anyway, if I take a box that's completely sealed of air, I have a certain amount of air in there, how many ever molecules I have. And if I then stretch that box, which ignoring the fact that's not possible, if I then stretch that box to twice the size, the density of that air in there is now half.
Yeah.
Because it's got twice the volume, same mass essentially. So the density is half. But as space expands, and I actually haven't even said that yet, but as space expands because of dark energy, it's not like you're taking a volume of normal matter and expanding it, because dark energy is the energy of empty space. So if you have a new piece of empty space, it has its own dark energy.
Okay, can I ask a stupid, crazy question?
Go for it.
Is it possible that energy could be fed into the system from a different dimension?
Sure. So that's a good theory, but to make it a scientific theory, you have to be able to test it.
Well, oh, come on. How?
So,
There's no empirical evidence of
There's no, yeah, exactly.
so in the case of all three of these, what these theories are astrophysicists much smarter than me coming up with their best rationale for why we're seeing what we're seeing. And until we can test them in some way, they're not really good scientific theories because you're not testing them yet.
So why are they even called theories? In biology, we would call them a hypothesis. We would not call them a theory. So,
Oh, and I can answer that.
in science,
Only because I just read this.
You can't test it?
A hypothesis is your prediction.
Oh, no,
Yes.
no, it's not.
They actually are.
They're distinctly different.
Smart idea, but.
A prediction is an if-then statement.
You
If
have
my
a-
That
hypothesis
supports
is
your
true,
hypothesis.
then I will see this in my test. They're
All right,
two
so
very
I
different
cannot
things.
explain that, not being a biologist. So I cannot even relate, I'm sorry.
I mean, it just seems like if we came up with a hypothesis, but we couldn't design
But I
an
couldn't,
experiment to
so.
show it and do data and support it
But in,
or negate it,
What would you do with it?
call it a hypothesis.
but in biology, most of what we do can be empirical. In
Yeah.
physics, which astronomy is part of, you have the theoretical physicists that do the back of the envelope calculations, and sometimes they turn out to be true. And
And they make assumptions in some cases,
So-
right, with their math, because
But
they
they
haven't
still
been able
call
to
them
demonstrate it
theories. It's just
experimentally.
interesting that you call them theories.
Well, see, I'm sitting here saying, it's just interesting that you call them hypotheses.
No, they don't call them hypothetical physicists. do they? Because then we wouldn't have to accept Aaron as he
Touche.
I'm
could
not.
be disproven.
I'm an observational physicist.
Yeah.
So, I don't have to take credit for any of this. Anyway.
So Aaron, wait, I'm sorry, before you, oh, I'm sorry, Ron,
I'm just
please.
going to say there are parallels in all the fields. So for example, in art history and in literary history, people define modernity differently. Some people believe it starts in what we call the Renaissance.
Oh, yeah,
Some
wow.
would say the 20th century. It depends how you define the terms.
A lot of times it's where the experts in a particular field, they come together in these conferences and they'll decide together what they mean in our field.
Yeah.
Well, the astronomers and biologists aren't sharing these conferences, so they're coming up with their own nomenclature and so on.
Believe it or not, I've never been to an astronomy conference.
Awesome.
They're so.
Never been.
So,
Okay.
Aaron, can I ask one quick question? I know this is, but, okay,
One?
I know, no, 27. But here's the deal, so energy, can you relate this back? I know you talk about it being homogeneous, but are you saying that the universe is not expanding all at a consistent rate?
No, that's not what I'm saying.
What do you say?
What I'm saying
Is it?
when we look at, as far as we know, at this current time, it's expanding at a set rate.
Okay.
That's a future slide, so
Okay,
we'll get
all right,
there
all
and we'll talk about that more. What it is saying is every chunk of space, no matter where you look right now, so keep in mind when we look at something that's very far away, we're looking back in time, so that's part of the things that's coming up. However, if you were to look right now at any sample, any piece of space, that dark energy is the same, and we see nothing that implies it changes
Okay.
from one place to another, which matter density and energy density do.
Yeah, it's interesting.
Okay.
That just means it's even more mysterious. All right, so why do we think it's out there? So I had to go back in history a little. So what happened was Einstein came up with his theory of relativity, which is profound, and like so many other scientific theories, it was wrong. But it looked good. It made a lot of sense after people studied it for a very long time, because initially it didn't make sense to any but probably two physicists. But okay. But it turns out it made sense. He put a fudge factor in there.
See what I'm talking about? They have to make the math work sometimes when they're math. Oh, no offense. Okay, so anyway, I'm just saying.
Yeah, I resemble that.
I know.
He put a fudge factor in because Einstein was convinced that the universe was in a steady state,
Yeah.
as most physicists were at the time. So he had blinders on. He couldn't see outside of that tunnel vision that we're in steady state, so he had to put a fudge factor in to make it work. And a lot of people say, based on the very next burger dot, that was his biggest blunder. His biggest blunder was not putting the fudge factor in. The biggest blunder was he discovered that the universe was expanding and didn't know it.
Yes.
That's a much bigger blunder.
Bring it on. Come on, Aaron.
All right, so in 1929, so that was about 100 years ago, 1915. In 1929, Edwin Hubble, one of the great observers of at least the recent century, discovered that the universe was expanding. And based on that expansion, he was looking at very, very distant objects, and yep, sure enough, it's expanding. And so he removed the fudge factor, and magically it worked without the fudge factor. Okay, and he was looking at the redshifts of distant galaxies. So as things move further and further away, they tend to be moving away from us because of this expansion of the universe. And as it expands, it takes those electromagnetic waves that we see and stretches them so they turn more red than they were. So that doesn't mean they all turn red, it just means a blue one is a little bit redder but still blue in most cases. Anyway, that was all good. Einstein died somewhere in here. And what then happened is these three guys, I'm not going to try to pronounce names, discovered that the expansion was accelerating. This was a big problem. And they had to put the fudge factor back in, opposite sign. And I mean, just, what can I say? But it was clearly accelerating. And what they were studying was the brightness of distant supernovae. So really large stars. Well, it's a different kind of supernovae, so we'll go with that one. When you have a white dwarf star, that's what will happen to the sun 5 billion years from now. You'll end up with a white dwarf. But if it's in a binary system with a larger star, that's still a star, that larger star will start sharing matter. And as it shares matter, eventually that little white dwarf will explode as a supernova. It just gets too heavy, it passes that 1.4, and it just has to explode. Very destructive explosion. Anyway, but it's always a certain brightness. Well, they were looking at these and they discovered they're 25% lower, give or take, than they should be, as far as that brightness is concerned. And they had no reason for it. And that's also because of this accelerating expansion, excuse me. So there's some evidence that says it's expanding. We don't know why it's, well, one thought is you say, well, we had a big bang, so it exploded and it's expanding. Well, okay, that's fine, but that doesn't explain why it's accelerating.
Right. You'd have to
So-
keep putting energy into the
Yeah.
system.
Yep. So this is what it looks like, right? Everyone loves graphics. So Big Bang's down here. We talked about studying supernovae, so that's as far back as they could go. This is where we are today with all of our fancy galaxies. But if you were to imagine the size of the universe, it's accelerating nice and smoothly here, but we're right on the cusp of it expanding at an accelerating rate. So it's getting faster and faster, bigger and bigger. The sad thing is that means eventually all the galaxies we see, except the really close ones, are going to disappear because they'll be too far away for us to see them, which is really sad. So we live in a really good time.
Just need better tools.
No, because they will expand to the point where they're further out than light would have had time to come to us. So they literally will
So-
just blink out.
We need to go further out. So that's
Okay. I like your thinking.
time travel.
Yes.
So there are some other things that we have looked at, such as cosmic microwave background radiation. It popped its head up again here. When we look around the universe, it looks very flat. And what we mean by that is it seems to be right at a critical density. And when you do the math, if it's a little bit off, let's say you've got a little bit too much matter or energy and therefore your gravity is too high, it would have already collapsed by now, back into a big crunch, which obviously it hasn't because we're standing here. If it's a little bit lower than that critical density, those distant galaxies would have already expanded out to the point where we wouldn't be able to see them, except for the local ones. Well, that hasn't happened either, because we can see all kinds of cool stuff. So, what that implies is, it is flat. The behavior looks flat, so we've got to be close to that critical density. It means we're missing a whole bunch of stuff. And the dark matter, which there's probably 6 times as much dark matter as normal matter, still doesn't give you enough. We're still way off. Okay. The second one is when we look at the large-scale structure out there, so we see galaxies, and we see clusters of galaxies, and when you get really big, what you see is ribbons of galaxies and voids where there are almost no galaxies. All of that, all those galaxies have not had time to form if the universe is only 13.8 billion years old, which is what we believe.
Sorry, this is so cool.
So,
Do we know how cool this is? This is so cool.
well, I do. That's why I'm talking about it.
I know that.
That's a real problem because they're there. We know they formed a long time ago, but we can't explain it. All right, and then the last one is the Hubble constant. This is the thing that you look at when you're looking at redshifts and the fact that distant stuff is very, very far away and it's moving away from us because the universe is expanding and that expansion is accelerating. And when they look at the age of the galaxies that they're seeing out there, and they compare that to those redshift values, which is how far away they are, therefore how long ago it was, they don't match. They've just got some real problems based on what we believe to be, kind of the life process that a galaxy would go through. So there are some real problems out here that dark energy, or the concept of dark energy, seems to take care of.
And you're trying to say that Goldilocks apparently is in charge of our universe.
Or the 3 bears are. So I like this because it kind of puts it in perspective. So normal matter, that's you, me, Earth, the sun,
Stars.
everything that we can see or relate to, is 4.9, so 5% of everything that has to be out there for us to be close to critical density. So we're going to call that X. So I'm going to do some algebra if that's okay.
Woo!
I'm sorry. Dark matter is about 5 times as big as that, right? So 27% or so. And if you look at that, that's only 5.5 times X. But that's a lot. That's a lot of stuff that we can't see, we know nothing about other than it's causing gravitational effects. But then if you look at the dark energy, to get us to that critical density, it's got to be 68% of everything out there in the universe. And if you think about it, if it's the energy of space, even though it's going to be very low level, very small, very weak, it's everywhere, and so everywhere is a big place. And when you add all that up, it gets to be a pretty big chunk. That's a full 14 times the matter that we can see. So those of you that are bothered by me converting energy and mass without talking
E
about it,
equals
that's
MC squared.
E equals MC squared. So
Einstein
no
was
more
wrong.
math. Sorry, I'm not going to go into that. But they're doing an energy-mass balance as opposed to just mass balance.
Okay.
That's a lot of missing stuff. So that's kind of what's going on and what everything is made of. So, and I love this line. I made this up. This is original. And I'm going to have to read it because I couldn't say it without reading it. In astronomy, what we know we don't know greatly exceeds what we do know. And imagine what we don't know that we don't know we don't know.
Yay!
Anyway, that is it. Is there any questions beyond all the wonderful questions you've been asking? Thank you very much.
So you mentioned about the distant supernovas, and they're 25% dimmer than they should be. Has there been any investigation that maybe they are that way because we don't completely understand supernova physics, and maybe the brightness isn't what we should be because of the way they're actually behaving?
So there is the type of supernova that I described is a supernova type 1A. And because we know it's caused by a white dwarf that meets that critical Chandrasekhar limit, we can predict what that absolute brightness has to be. It's minus 19.3. Incredibly bright. It will outshine its entire host galaxy while it's doing that thing. So that one we're really confident about. You can study the light curve as it dims and goes away and know which one you're looking at because they're very characteristic curves. So absolute, we've got pretty well on those, and I'm sure that's the type they were using. The other supernovas where you have a giant star that explodes, those are all over the place because it depends on the mass of the star. What, in my mind, could be questionable, and I have an example, personal example, is the apparent brightness. Because you're comparing apparent to absolute, and I'm willing to say absolute is absolute, but the apparent depends on a whole bunch of things. And my experience with that was I was doing a supernova. I was tracking its brightness as it decayed at the observatory. And as I did that, I was looking at it. I knew what the absolute brightness was, and I can do a little bit of math. So I did the math, and I said, in a newspaper article, I said, I expect it's going to get this bright and should be naked eye visible. Boy, was I wrong. And the reason I was wrong is I didn't take into account, and I don't know how astrophysicists do this, but I didn't take into account
You didn't put a
dust.
fetch factor in?
Well, no, I didn't take into account the dust. If I were seeing just that supernova, my calculations would have been perfect. Maybe a little off for our atmosphere, but in general it would have been perfect. The problem was, it's in a galaxy, it was almost edge on. There's a lot of dust between me and that. So I have to assume they have some kind of a fudge factor that they apply to take into account that dust. But that's where I would think the error would be, unless, as you actually surmised, possibly we just don't understand it. But we don't know any reason why it would be different just because it was 12 billion years ago. So good question. Yes?
In this slide you showed before that shows the expansion,
Yes?
you have an inflation and then slows down.
Yes.
And then makes a jerk there and then accelerates again right there.
Yes.
So during half, like 7 million years ago or somewhere around that, it was actually collapsing. It was like slowing down
Yes.
and then started accelerating again. Do you determine this just by looking how far those supernovae are and then using the same
Okay,
method?
so
How do you do
good
it?
detail. What do you teach?
Physics.
Okay, I was wondering. That was awfully detailed. Good job. So the problem is we can easily see back to the early supernovae. That's not a problem. We can see back beyond that to see some very primitive galaxies. The Hubble Deep Space Image has pictures that you study the redshift and you can tell how far back in theory it is. And that goes back till about, don't quote me on the number, but about 800,000 years after the Big Bang, maybe a little less than that. The Big Bang itself started, in theory, and the universe starts expanding, and then there's an inflationary period that goes on. It happens between 10 to the minus 32 and 10 to the minus 35 seconds after the Big Bang. So there's a lot of zeros before you get to the number. We can't see that far back. So it's hypothetical. It's what we believe should have happened. Why we think it happened is because of something called, I should get the right one, the horizon problem. The horizon problem is we look this way and we can see, call it 13.7 billion years. We look that way, we can see 13.7 billion years. Well, that's a total of 27.4 billion years. And the problem is when we look, the cosmic microwave background radiation, that's the same temperature as that is. And because of thermodynamics, if they're the same temperature, they had to be communicating at some point. They're too far apart to have communicated. So in order to get there, that means you had to start where they were communicating, and then there had to have been a period where things went nuts and it inflated. The dark energy theorists are saying it's probably related, the same energy, dark energy. But we don't know enough to put numbers down yet. But yeah, so it did expand, then it went back to its normal rate, which I assume is the same rate as down here at the bottom. But as things move further and further apart, and the reason why it's accelerating is now you have big chunks of empty space, which means there's nothing there to fight dark energy. And there's not enough gravity to fight it. The reason we don't have a problem inside our cluster of galaxies is we're gravitationally bound. Gravity is strong enough to hold us together.
Okay, so, I mean, the phase from slowing expansion to accelerating expansion, we're sure of that because of what kind of observation? That's what I was trying to understand.
Yeah, so sorry. So going back to about
Okay,
here,
exactly.
we can see that's historical, and just by looking at galaxies that are further away, we can tell
Okay.
how fast they're accelerating away from us, and that implies what rate that expansion has been going on.
Okay. So before 1998, we knew about this part. It was
Yes.
slowing down, or about right there where it was slowing down or constant.
Well, and it's worse than that. I didn't bring that slide, but so take my astronomy class because it's there. But prior to that, we did not know what the history of the universe looked like. And depending on how you draw that picture, this is one of them, but depending on how you draw that picture, the Big Bang happened at different times in the past. And this one is the one that implies the furthest back, 13.8 billion years. But it could be steady expansion. It could be expansion that's slowing to some asymptotic value. We didn't know. But when they studied the expansion, they started getting data that implied this is what it's doing. And we have started into that expansion accelerating. And so we don't have the future data, obviously, but they have just enough to say this is where we're going.
But something made that jerk from slowing to accelerating,
Well-
and maybe it's going to happen again, maybe?
I have no idea. I've not heard anything that was proposed.
Is the thought that you could convert, like if you have energy and matter being converted, could you have converted more matter to energy and created an expansion, a greater acceleration that way?
But who's doing the converting?
Well, okay.
Right now, the only
That brings up
conversion
a
we know
whole other can of
of, except
worms.
what we try to do here, is in the heart of stars. And it, blows the stuff all apart when it runs out. But, that's it. We don't know of anything that would cause that.
I agree. But it happened, or something's going on.
Not clearly, yes. Any other questions? I don't have an answer. Now I ask you.
He's not flying to Stockholm.
Cool. Okay.
Well, just a couple observations from my perspective, which is not scientific. It's an old bromide in literary theory that there's no such thing as negative imagery. It's contradiction in terms. But this would seem to suggest that that's not the case, right? And then it also suggests that, as has often been observed in the history of theology, the most interesting arguments for the existence of the divine is our kind of argumentation we call negative argumentation, the ontological argument. What are you talking about?
He talks about that all the time.
So anyway, that's just an interesting parallel here from outside of the science.
Well, think about it though. You hear, like, honestly, people who have spiritual beliefs, you know, they talk about something that you can't see but has an effect, and they feel this effect in their lives or whatever. And you say, "Oh, you guys are crazy," and then the theoretical physicists come along and say the same thing, but they're scientists. They're, you know, do you see? And I'm just saying, I'm just.
And my response to that, so I will not pick on anyone's beliefs. And what I tell my students is I'm not here to tell you what to believe. I'm here to tell you what you need to know to pass the test. So this is the end, you know, like, for example, 13.8 billion years. You got to know that number or you're not going to pass the test.
That's right.
But you don't have to believe it's true. You just need to know it. The difference is theory versus scientific theory. Sorry about the hypothesis thing. But theory versus scientific theory. Things that are based on faith do not have to be tested and are not continuously tested. So that would be my answer to what the difference is. Now, are they right? I have no idea, because there's no way to prove it one way or the other. So I'm not even going to go into that argument. But.
Yeah, and there are certain theories that just based on our point in technological development that currently can't be tested, like string theory being another one.
Perfect.
And so there have been arguments about, well, sometimes when you're in that period of time, when you have these theories or hypotheses or whatever we want to call them, when you can't test them, there's a very fine line between that and faith. So it's things like the multiverse. I saw an article about, well, the existence of the multiverse, even by scientists, is kind of an act of faith, even though it does have explanatory power for certain theories.
Some of us don't have that faith, but okay.
Right, exactly. But, yeah, we're waiting to be able to.
And that's okay, right? That's,
I mean, but if I were in a position to do so, it would be my job to come up with a way that we can test that that's wrong.
Right.
Agreed.
I don't have that capability, but if I could, that would be my job, my responsibility.
But you have to admit, when you get down and you start talking about what happens on the quantum level and that everything's possible, nothing's possible, this is possible, but then this is possible, you know what I mean? I mean, that gets into a whole realm of wackiness that, you know, sounds a little crazy, right?
But most of that wackiness has been tested and shown to happen.
I don't dispute that,
So,
but it's still
it is
wacky.
wacky, yes. The last lecture in my class that I try to do every semester is on reality and relativity. And that's what we talk about, and I have a picture in the middle of that of some scientist holding his head saying, yeah, this is about the point where I got the headache too. So, because a lot of it is very bizarre. It's counterintuitive, it does not make sense in what we see day to day. So, yeah, very true.
Well, thank you very much.
Thank you. Thank you.